Hello everyone, welcome to lesson 4-7, linear and nonlinear functions. As we continue to address the question, how can we model relationships between quantities, we will look at the vocabulary nonlinear function. We can use the context of football to talk about nonlinear functions. The table shows the approximate height and horizontal distance traveled by a football kicked at an angle of 30 degrees with an initial velocity of 30 yards per second. Is the rate of change for the height of the football constant? Now think about this. As it's going farther and farther up, it should slow down, right? Because gravity starts to take force. So at 0 seconds, we have 0 height and 0 distance, correct? But at half a second, we've got a height of 6.2 yards and a distance in yards forward away of 13 yards. At 1 second, so the time has doubled, it has not doubled in terms of height. Notice that it probably went up by about 50%, while here went up by 100%, right? It doubled, went up by 100%, but here only about 50%. But the distance is still, it is still doubled. Notice that in height, again, when we add another half a second, in height, it really only went up by about 1 yard, while in distance it's still traveling and tripling. So it's traveling at a constant rate of change of 13 yards per half seconds, or you could say 26 yards per second. And 26 plus 26 would be 52. And it looks to be like it's traveling, the distance is linear, if you can see that, but the height doesn't seem to be linear. It's definitely not linear. It changes every time. So is the rate of change for the height of the football constant? The answer is no. In the first half second, so in the first half second, you can see here, the ball's change in height was 6.2 yards, right? It went up 6.2 yards from here to here. In the next half second, the ball's change in height was 9.7, so it only changed by 3.5 yards. So even though from here it went up by half of a second, it only went up by 3.5 yards. And then again, when we add another half a second, it only goes up by, it looks to be like 0.8 of a yard, right? It's not even a whole yard. So it is not a constant rate of change. Number 2, is the rate of change for the distance traveled constant? Well, it looks like half a second is 13, a whole second is 26, half a second is 39, and then another whole second is 52. If we were to count by seconds, 1 second is 26, which means 2 seconds should be double 26, and it is, it's 52, right? So there we do have a constant rate of change here. So, yes, the football travels a distance of 13 yards each half second. Number 3, graph the ordered pairs, time and height, and time and distance on separate grids. Connect the points with a straight line or smooth curve, then compare the graphs. So for the first graph, we're going to do time and height. And you know that this one is the one that does not have a constant rate of change. While the second one is the distance and the time. This one does have a constant rate of change. So we should see a nice straight line in this one. And in this one, we should see a curved line. So when we start to graph, I know, let me zoom in. If you recall from the graph, the first point was at half second, right here, at a half second, it traveled 6 yards, right? Let's see, I'll go back to it. 6.2 yards, okay? There it is, right there. 6.2 yards, so it's gonna be close to 6. Here it'll be 9.7, so close to 10. Right here it'll be, again, close to 10, but halfway to between 10 and 11, and so on. Okay, so those are the numbers we have to use. So I will go, again, zoom in. And I know that it's slightly over 6, so I'll put it right there. Okay, 6.2, and then we said 9.7. At the 1 second, 9.7 will be close to there. Okay, almost at the 10. And then 10.5 or so. And then it starts to drop. I remember just slightly above 8, and then just slightly above 4, right? Just slightly above 4 in the next half second. And that's how much it traveled in 2.5 seconds. And if I were to draw a line, okay, we do know that it all starts at 0, 0. It would go up like that. A nice curved line, and then down. And then you can kind of see that when a ball is kicked, it's similar to this trajectory. Okay, maybe a little more curved than this, but it looks like the trajectory of a ball. For distance, again, we're using the increments of half a second in time, but in distance, we're going to mark them. We're going to use increments of 10 because it increases 13 yards every half a second. So the first one should be just slightly above the 10, right there. And then for the full second, it should be at 26. So between 20 and 30, right about there, right? And then the next one is 39. Okay, 39 just below the 40 mark right there. Okay, the next one is 52. At 2 seconds is 52, just above the 5 there. And then the 50. And then at 2.5 seconds, we have 65. So between the 60 and the 70, about there. And if I were to draw a line, it would be a nice straight line that would continue upward like that. So we could put our arrow there. So this would be a nice linear function. So in my observation, I would say the graph for the height of the football is a curve, and the graph for the distance is linear. And for one of our key points, we're going to address the vocabulary of nonlinear functions. So what do we mean? In a previous lesson, you learned that linear functions have graphs that are straight lines. This is because the rate of change between any two data points is constant. Nonlinear functions are functions whose rates of change are not constant. Therefore, their graphs are not straight lines. Now let's look at these two examples and determine whether each table represents a linear or nonlinear function. And we will explain, okay? Well, the answer's been done for us. But let's look here. Our input is +2 each time. And our output will be -15 each time. So this looks to be linear. It's not proportional because it doesn't start at 0, 0. Or it could, I guess, if we knew a little bit more about what this data represents. But we do see that it's a linear function because they both change accordingly. When this one changes by 2, this one decreases by 15. So as x increases by 2, y decreases by 15 each time. The rate of change is constant, so this function is linear. Let's look at number 2. Okay. Our input is 1. Then it increases by 3 to 4, and then increases by 3 again to 7, and so on to 10. On this side, when 1 is here, we have 1 here. Okay, they're both starting, it looks like they're both starting in the same position, but then when increased by 3 on this side, it increases by 18 over here. And when it increases by 3 on this side, it's going to increase, sorry, first not by 18, I made a mistake. I looked at the wrong numbers. I looked at this number to this number. It increased by 15, and then increases by 33, and then it increases by 51. So clearly, the change, the output, is not a constant rate of change. So there's no constant rule between these two, between the input and the output. So as x increases by 3, y increases by a greater amount each time. The rate of change is not a constant. So this function is non-linear. Notice that when they're both 1, okay, then it changes by it increases by 15 on our y axis, but then it jumps up by 33 and then by 51. So it's sloping up more and more, how should I say it, steeper, where the change is gradually becoming more steep. Okay, here are two tables for you to practice. Please take a look at the relationship between the x and the y on both and determine if they're linear or non-linear and why. right? Explain, and you would explain by simply outlining how the x changes and the y changes. Okay, so go ahead, pause the video and try A and B. Pause now. Okay, I hope you paused the video. Now let's check our work. We have an input here at 0, okay? When x is 0, y is at 20. Okay, so clearly this is our y-intercept, right? It's starting at 20. When x increases by 5, so 5 later horizontally, y decreases by 4. So over here we have an increase of 5 each time on our x-axis. And on our y, we have a decrease of 4 each time. So because the change is constant on both, 5 here plus 5 for x is -4 for y each time, we can say this is a linear function. The rate of change is constant. As x increases by 5, y decreases by 4. Question B. As x increases by 2, see, 2, 4, 6. Let's look at y. Y at 0, 0, which means it's a proportional relationship, but it's starting at both at 0. Then we both have 2, okay. But then over here, as this increases, as x increases by 2, y increases by 4. As x increases by 2 again, y increases by 10. So there's really no pattern. First 2, then it increased by 4, and then now it's increasing by 10. I don't really see a pattern. So this function is nonlinear. As x increases by 2, y increases by a greater amount each time. I should add in there a greater unpredictable amount. But really, just all we really know is that it's a greater amount each time. So it's going to curve. You see how this is? It's going to create a line that will curve more. It'll gradually get steeper and steeper because it's rising faster and faster. Example 3. Use the table to determine whether the minimum number of calories a tiger cub should eat is a linear function of its age in weeks. So here's the tiger cub, age in weeks, 1 week, 2 weeks, 3 weeks, all the way up to 5 weeks. And the minimum calorie intake it must eat as it grows each week. So in the first week, it should eat 825 calories. The second week, 1,000. The third week, 1,185. So how do we know if it's increasing, if the increase is constant, if it's increasing by the same amount each month, each week? What we need to do is we need to compare our y, our increase in y. So by simply finding the difference, so like y2 minus y1 here, or y2 minus y1, and so on. And that's what they've done here. They've taken y2 minus y1, okay, the second one, and they see that it was an increase of 175. But then the next increase was an increase of 185. At the third week, it only increased by 135. Then on the fourth week, okay, on the fifth week, it only increased by 100. You can see it here from 45 weeks. Okay, so this is not a constant rate of change. Each time the amount that it's increasing by is different. So the rates of change are not the same. Therefore, this function is nonlinear. Graph the data to verify the ordered pairs do not lie on a straight line. We could practice now by doing this one. Tickets to the old dance cost $5 per student. Are the ticket sales a linear function of the number of tickets sold? Okay, so let's see. Number of tickets sold, 1, $5. Number of tickets sold, 2, $10. Number of tickets sold, 3, $15. As each ticket is sold, then the ticket sales go up. The money goes up by $5 each time. This looks like it is a linear function. The rate of change is constant. As the number of tickets sold increases by 1, the total ticket sales increases by $5. Example 4. A square has a side length of s inches. Okay, so a square has a side length of s inches, which means, remember, a square has all sides are even, but here they're telling us that it's s inches. We don't know. The area of the square is a function of the side length. Okay, does this situation represent a linear or nonlinear function? Explain. Make a table to show the area of the square for a side length of 1, 2, 3, and 5 inches. 4 and 5 inches. Okay, so we're just going to make a square with each side 1 inch, a square with each side 2 inches, and so on. So what we're trying to say is, remember that area is length times width, right? So that would be the rule between our x and our y. So here's our x and here's our y, right? And if our side length is 1 inch, 1 times 1 equals 1. If our side length of a square is 2 inches, the area will be 2 times 2, which is 4. If a side length is 3, 3 times 3 would be 9. If the side length is 4, 4 times 4 would be 16 square units. And if the side length is 5, 5 times 5, which is area equals length times width, so our length times width would be 25 square units, right? Graph the function. The function is not linear because the points 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25 are not on a straight line. Of course it's not. As we increase by 1 inch on the side, the numbers have to multiply into one another, and it's going to become exponentially larger, which means it's going to gradually become more and more steep. You see that? Gradually steeper, more vertical. And finally, we're down to our last example where we can practice what we just did on example 4. A square has a side length of s inches. Again, we don't know what the side is. The perimeter of the square is a function of the side length. Does this situation represent a linear or nonlinear function? So now we're looking for the perimeter, not the area. Okay, now we're looking for the perimeter. So again, we have to choose, right? Let's just choose. If we have a side length of 1, where x is represented by 1, okay, then that means our y will be 4, okay? Because just if one side of the square is 1 inch, as you can see here, 1 inch, so that's my side of the square. My other side of the square is another 1 inch. My other side of the square, this is not really much of a square, it's looking more like a rectangle, but you get the idea. And then finally my other side is another 1 inch, okay? When I add all the length to find my perimeter, I have 1, 2, 3, 4. So it's 4. So if it's 1 inch, the one side, my perimeter will be 4. If it's 2 inches, it'll be 8. Right? 2 plus 2 plus 2 plus 2. If it's 3 inches, it'll be 12. If it's 4 inches, it'll be 16. If it's 5 inches on each side, it'll be 20. Okay, so let's see. As it increases by 1 inch in my input, it increases by 4 in my output. So what do we say about this? We would say that it is a linear function, correct? The function is linear. If you graph the function table that we have here, the order pairs, so 1, 2, 2, 8, 3, 3, 12, and so on, which is the side length and the perimeter, they lie on a straight line, or you could say they make a straight line. So therefore, it is a linear function. Okay, and here's our guided practice. This is how we will start our next class. Please take a look through the examples or what you are expected to know or feel comfortable with when you get to class. If you have any questions, please bring them to class. See you then.